Hi, everyone. My name is Pranav, and I'm joined here with Arjun, Brian, Christopher, and Matthew, and we're here to talk to you about our project, Saffire. We started off this project by examining a key statistic that at $5,000 per pound, saffron is the world's most expensive spice, and we asked ourselves, is there an engineering opportunity here? For some background, saffron is an internationally coveted spice for the flavor it brings to many cuisines, its cosmetic uses, and its medical uses. Today, it's harvested in three steps. First, the flowers are picked by hand from the field they grow in. Next, workers work to separate the spice strands from the flowers that they grow in, and finally, those strands are dried in bulk for shipping. The most labor-intensive part of that process currently is separating the spice strands from the flower they grow in. Each flower contains just 3 strands of spice, as shown here. Now, those numbers quickly add up when you consider a whole acre of this spice. Each acre contains 680,000 flowers, which are currently sorted by hand. This produces about $20,000 of retail value of the spice, but remarkably amounts to 700 labor hours per acre, 75% of which is the act of separating the spice from the flower. Now, 95% of the world's saffron production today occurs in Iran and Spain in very low wage conditions. Recently, however, there's been a push to expand domestic saffron production. Today, a lot of the saffron farms in the United States are limited to 1 acre because there's no automated means to harvest the saffron flower. And that brings us to our problem statement, that a lack of automation makes processing saffron prohibitively expensive domestically, and that's where we hope to come in. Now, to date, there has been some work in this area which represents partial solutions to the problem. For example, at the University of Valencia, they leveraged aerodynamic properties to separate the spice from the flowers that grow in. They also developed a cutting mechanism and other aerodynamic work to separate the spice, but none of these represent a complete solution. Now, that's where we hope to come in. We propose an end-to-end solution where you pass in the unsorted flowers into a machine and collect the spice on the output end. In order to determine whether we're successful in creating this machine or not, we will evaluate it against the following system characteristics. First of all, concerning the volume that this machine occupies. It has to fit within a 15 by 5 by 5 foot plan area, and it's got to require less than 4 hours a day of human interaction to make this financially viable. Furthermore, it's got to be able to operate at less than $5,100 per acre and be able to operate continuously for the 4-week harvest over which saffron harvesting occurs. Finally, we've got to be able to recover 95% of the saffron that we input into it, and the discoloration of the strands has to be minimal, and we need to produce the highest quality of saffron on the output end. If we are able to achieve all these characteristics, we will have made the large-scale domestic production of saffron viable. Now, I'm going to pass it off to Arjun, who's going to talk more about the design and engineering of our machine.
Thanks, Pranav. And now I'm going to talk you through the design and engineering of the overall system. Here, you can see an example of what a user might interact with when working with our machine. They would input a bulk of flowers into the top. These would traditionally have just been picked from the field. At the bottom, they would remove the desired product, the saffron stigma. Occasionally, the user would also have to remove waste products, which in this case are the flower stems and the flower petals from the machine. Our machine has 5 main subsystems, the first of which is the input vat. A user dumps flowers onto the input vat, and then these disperse the flower onto the orientation mechanism below. The orientation mechanism has a series of triangular troughs that oscillate up and down in order to orient the flower with the stem facing downwards and the bulb facing upwards. The cutting mechanism has 2 main parts, the blades and the fans. The blades traverse beneath the orientation mechanism and cut the flower at the base or the vertex, where it splits into 3 separate parts, the stems, the petals, and the stigma. The stems are caught by the cutting mechanisms themselves. The stigma and petals remain in the troughs, where the fans will blow over them, forcing them through the orientation bed into the separator mechanism below. The separator mechanism features a fan and a conveyor belt that utilizes the difference in aerodynamic and geometric properties to separate the stigma and the petals. Here you can see where the stigma and the petals would be collected in the overall machine. Now to talk through the technical details and design of each system. So starting with the input vat. It travels using the sliding mechanism that we've designed along the 80-20 rails. Once the flowers are filled into the basket, a series of threaded motors will control the motion and dispersion of the flowers. The red pusher will elevate the level of flowers overall, and the blue pusher will push flowers through the outlet shown. I'm now going to hand it over to Brian to talk about the orientation mechanism.
Thank you, Arjun. So after this input vat distributes the flowers over the bed, we design an orientation mechanism to align the flowers stem down within a series of vibrating troughs. From the geometry of the flower and the accelerometer experiments we did by hand, it was determined that the vibrations with an amplitude of 10 millimeters and a frequency of 5 hertz would do the trick in orienting the flower. Starting with the troughs, we wanted to orient and translate the flower to a cutting zone. In our initial experiments, we encountered a relatively high coefficient of friction between the flowers and most materials, so we first focused on methods to translate the flower. First, we tried an air-based system to reduce friction, but due to the compliance of the flower, even with high pressures, we weren't able to reliably translate it. Next, we tried conveyor belts on the face of each trough, but due to geometric space constraints, it was not feasible to actuate the belts effectively. We finally considered a design with moving troughs, but this had the potential for the flower to become unoriented. Ultimately, we decided to integrate the cutting mechanism directly under these troughs, removing the need for flower translation. So the final form of the trough system consists of aluminum sheet metal triangular vanes mounted on an oscillating bed, with gaps between each vane for the cutting mechanism to operate on the flower's vertices. The source of vibration for the orientation mechanism comes from an in-house slided crank mechanism consisting of a motor attached to a rigid arm set to the length of the desired amplitude. This arm rotates, which pulls the bed with a string linearly constrained by a hole in the bed against a series of springs. Based on a first-order static simulation, using specified spring and motor characteristics, we chose a configuration for our system that minimized costs while still achieving the desired motion. This approximation was later refined and confirmed using a dynamic simulation. Now, here's Chris to talk about the cutting mechanism.
Thanks, Brian. The next step in our machine is to cut the flowers to create a mixture of stigma and petals which can be separated. During our preliminary research, we found that there's a 3 millimeter tall zone on saffron flowers where an incision would separate the petals and stigma from the stem. As a result, we designed a gap in the bottom of the troughs to allow the flower's vertex to protrude, which can then be cut by the cutting mechanism. The cutting mechanism sits on top of a series of motors and wheels that slides along aluminum rails, providing 2 lateral degrees of freedom. On top, 4 rotary blades are positioned at the flower vertex height to cut the flowers as the mechanism moves. Here's a top-down view of the cutting process. The mechanism would align the blades by moving in the lateral direction with a set of troughs. Then it will move down the track and cut the flowers. Finally, the mechanism repeats the process for the next set of troughs. This mechanism had 2 primary design challenges. The first was that the motion of the mechanism was not smooth due to misalignment of the third idler wheel. The second issue, shown here, was that the 2-blade cutting designs failed due to compliance of the flower stems. To solve these issues, we removed the idler wheel and implemented a single blade system which relied on a 3D printed structure to provide the reaction force necessary to cut the stems. These 2 design changes can be seen in the images here. Once these changes were implemented, the cutting mechanism was complete, which leads us into the final subsystem, the fan-driven separation mechanism. The most efficient method of separating petals from stigma involves leveraging the differences in aerodynamic properties of the 2 components to separate them via airflow. Our first prototype relied on a fan-driven air duct. The idea was that after being blown through the duct, petals would fly out and land further away than the stigma due to their increased drag. The first step in this process was to model airflow through the duct. Using COMSOL computational fluid dynamics, we modeled the velocity fields for fan-driven flow at 3 different speeds. A velocity chart is depicted here. Using this data, we then simulated the trajectories of petals and stigma using 2-dimensional drag based on the velocity fields that were exported in from COMSOL. This allowed us to produce theoretical landing locations for the 2 components. When we tested our first prototype, we found that the fan was powerful enough to propel the components up and out of the duct. This resulted in a roughly 2-foot landing zone for the stigma. Unfortunately, the petals did not land as reliably as the stigma, and there was no discernible pattern in their landing locations. To fix this, our next prototype was designed to limit the effects of chaotic projectile motion by constraining petals and stigma on a moving conveyor belt. The idea was that in this design, the stigma and petals could be dropped directly onto the conveyor belt. As the conveyor belt moves toward the fan, the drag force experienced by the petals would propel them backwards off of the duct, while the stigma remain on the belt and pass under the fan into a collection bay. This solution proved much more reliable than the duct system and was eventually chosen as our final design. As shown here, a collection bay affixed to the end of the conveyor belt will collect the stigma, enabling farmers to retrieve them. Now I'll pass the torch on to Matt to discuss validation of our machine subsystems.
Thank you, Chris. As the designs of the subsystems were being finalized, it was important to test and validate each one individually before full system integration. For the orientation mechanism, both the orientation and vibration of the flowers needed to be tested. In the video on the left, you can see a flower fully oriented between two aluminum troughs. And in the video on the right, you can see another test flower vibrating with an amplitude of a few millimeters. Between the success of these two baseline tests, the team was confident that with the addition of a full bed of troughs, this orientation mechanism can handle a high throughput of flowers and be ready for full integration with the rest of the machine. For the cutting mechanism, both of the design challenges cited earlier were tested. In the video on the left, you can see that with the addition of a 3D printed wall to provide a higher reaction force, a much cleaner cut was achieved at a given location in the flower. In the video on the right, you can see that with the removal of one of the driven wheels, a much smoother lateral motion was achieved by the cutting mechanism. Between the successes of these two tests, you can see that the cutting mechanism was ready for full integration with the rest of the machine as well. For the separation mechanism, two tests were conducted after the relatively disappointing results of the vertical separation mechanism. In the video on the left, you can see that most but not all of the petals are separated from the stigma. This gave the team the confidence to move on with a horizontal base separating design. And with the addition of a conveyor belt, as seen in the video on the right, the team was able to achieve near 100% separation and collection of the saffron stigma from the petals. Thus, this subsystem was definitely ready for integration with the rest of the machine. The final test was an economic validation, which was particularly important to our stakeholders, as well as it influenced a number of our system metrics. The four costs that went into this validation test were the associated labor costs, which was an estimate from the average US farmer's wages, the cost of power, which was an estimate from running our machine for a given period of time, the depreciated cost of our product per year, which was a 10-year depreciation cost of an approximated consumer version of our machine, as well as the cost of picking and harvesting the flowers, a task the farmers still needed to do in order to bring the flowers to our machine. These four costs amounted to just over $2,400 per acre, much less than the $5,100 per acre system metric. And thus, Saffire could potentially be a profitable solution for US farmers. Although we were unable to achieve full system integration, there were a few tests we would have liked to conduct in order to hit some of our other system metrics. The first test was a separation percentage test, where we would compare the outputted mass of stigma to the inputted mass of flowers and get a better estimate to the overall efficiency of our machine. The next would have been a saffron quality test, looking at the quality of the outputted product and comparing that to industry standards and adjusting our machine accordingly. The final test would have been a timing test, where we would look at the interfaces between the subsystems, adjust the motors and the speed at which things operate, and then get a better estimate to our power draw and thus our cost of our overall machine. With that, I would like to give a special thanks to all those who helped make this project a success this past year. To our primary faculty advisor, Dr. Rainey, to our three technical advisors, Dr. Kumar, Professor Albert, and Dr. Wabachevsky, to our two awesome TAs, Ali and Anthony. We would like to also thank our two external stakeholders from the University of Vermont, Dr. Arash and Dr. Skinner, and the manufacturing team of Peter, Pete, Jason, and Joe. Team Saffire aims to automate the saffron industry, thus making the domestic production of saffron economically viable. Thank you for watching, and we look forward to answering any questions you may have about our project.